Good morning. Our thanks to the organizers for this opportunity to be present at this tribute to Gaspar. Gaspar contributed to many pillars on which LIP is constructed. One of them, detectors and instrumentation, because he knew what Freeman Dyson, one of the most distinguished living theoretical physicists, formulated so aptly. New directions in science are launched by new tools more often than by new concepts. Gaspar's vision was to advance instrumentation in order to advance science, to make LIP a world leader in instrumentation, such that it would be a world leader in research. And he concentrated on a few of the most promising directions consistent with the talents and interests of the staff of LIP and the infrastructure. And as mentioned already many times today, he was conscientious that fundamental science must also pay something back to society. And yes, he managed remarkably well to involve Portuguese industry. We just use a few examples to highlight his vision. One is the detector development in gaseous detectors. Long before LIP existed, there was a world-famous school of gaseous detector development in Coimbra, and it was natural to build on this competence on this school. And I mention just one example here, resistive plate chambers. This was an old technology, was using bakelite plates covered with some electrodes, and where an electric potential produced a spark every time a particle went through. Well, this was developed to a large extent at LIP into several areas where very important contributions was made. One of them was the development of high-performance, high-resolution timing RPCs. This is an early contribution, a large detector, to an experiment at GSI, the hardest time-of-flight wall. And you see here this remarkable resolution of about 60 picoseconds, but not just in one channel, over the whole detector. This is for all the detector channels, showing the same kind of remarkable resolution. This was a renaissance in the technique of identifying particles by time of flight, and LIP made major contributions to that. Another area was to develop these chambers, which are relatively cost-effective and simple to construct, into chambers which work by themselves, basically. Just a little bit of gas, and they would work for months or years unattended. This picture shows, This picture shows one of these typical chambers. They seem simple, but a lot of intriguing, ingenious engineering went into the construction, the development of these autark chambers. Here you don't see them because they are below one of these detectors, a few tons of water Cherenkov in the Argentine pampas. Ultimately, the aim is to make sealed chambers which would revolutionize cosmic ray physics. I like this graph because it shows how LIP RPCs are covering the planet. Now, not only can you detect charged particles, you also can detect neutral particles, for instance, neutrons. This has become a very active area of research because detectors for thermal neutrons based on helium-3 are on the way out because it is very difficult to get hold of helium-3. So one of the concepts being considered at LIP is coating RPC planes with boron-10 using the N-alpha reaction to detect thermal neutrons. And this picture shows here a stack layered of RPC layers and the detection of neutrons. And there again, you take advantage of the very high spatial and temporal resolution to make these novel neutron detectors, which, for instance, will be used, if successful, at the European Spallation Source. Another area is medical imaging. We heard about already PET instrumentation using crystals, but here's an attempt to use this technology to detect the photons from the 511 kV photons from annihilation, positive annihilation, to image tumors in the human body. It started with a small prototype to image animals and has been used routinely for the study of medication, but the next step is to build a device large enough to image the human head. And this is an effort going on where, again, one uses sub-millimeter space resolution, 100 picosecond type time resolution to build a novel instrument with the promise of reducing the cost of these instruments in a significant way. Now, if you have competence in gaseous detectors, you might think about developing competence in noble liquid detectors, such as liquid xenon and liquid argon. And this challenge was taken up by the groups in Coimbra, who over the years pushed R&D in liquid xenon detectors to new levels, which allowed them to participate in major ways to dark matter searches, as mentioned earlier today. One experiment, Lux, in which the Coimbra group made very important contributions, held for many years the world record in sensitivity on these WIMPs as a function of mass. This, as we heard, is an extremely active and competitive area. They have now been superseded by Xenon 1 ton. The Xenon collaboration in Gran Sasso continues with N-tons. Lux is continuing with the next generation teaming up with another collaboration, Zeppelin, to build a 10-ton liquid xenon detector, which is presently installed and being readied for operation. Liquid argon is another frontier where for neutrino detection, one is looking for very large masses in the 10 to 100 kiloton range. And there is liquid argon one of the prime targets of neutrino detection. What you see here is a prototype which has been readied at CERN. Now, this is only 17 tons, so you can imagine what 100 kilotons look like. But this detector has seen first charged particle tracks last fall. And LIBS involvement in neutrino physics allowed them to become partners in this very advanced DUNE experiment, which, as I said, aims for the 100 kiloton range of neutrino detectors. Now, having covered the area of accelerator physics, of course, it was logic for Gaspar to push the next frontier, cosmic ray physics. And LIB is a founding member of the world's largest cosmic ray ground-based facility, Auger, to which they contributed with hardware, but also with physics. And I would like to single out one very interesting physics result to which LIB contributed in important ways. It's the muon anomaly. What you see here are simulations of the shower depths, the start of the shower, as a function of the particle composition measured by a quantity related to the number of muons and the distribution of muons, R mu. Now, these are 4 different simulations, and this is the Auger data point, which disagrees with all of these simulations. Do we not understand the composition of cosmic rays, or are we looking at new hadronic physics? We do not yet understand at least 10 to the 19 eV energy range. This is so important that the collaboration has decided and got funded to upgrade Auger to improve the muon capability to follow up this intriguing result. Well, success, as we have heard, breeds success. In this case, a new concept for a new gamma ray facility in the southern hemisphere, an array of detectors aiming for sensitivity of 100 GeV to 100 TeV gammas Again, you guess it, with a large array of RPCs, ground-based, but this time they have to work at 5,000 meters. Imagine the temperature variations over the year and over night and day. A very challenging project, but where the LIP expertise and RPCs are being challenged. Moving from the Earth to space, where else? LIP was one of the founding members of the alpha magnetic spectrometer, which is housed on the space station. And LIP has actually been contributing to one detector of these very compact detector, the imaging Cherenkov detector, and has doing physics with this. I still remember the agony of the LIP Scientific Advisory Committee mulling over the interest of LIP participating in this detector. It had a very difficult gestation period, but Gaspar put aside all the worries of the committee. Patience and perseverance were hugely awarded. This experiment is successful beyond the expectation of most physicists who knew about this experiment. I just look at the fantastic precision with which particle spectra are measured as a function of energy, or this graph has already shown the incredible precise measurement of positrons. The low energy part around 10 GeV, that is understood. The high energy part peaking at a few hundred GeV is not understood. Is this an unknown source of astrophysical positrons, or is it actually the signal of dark matter particles annihilating? Time will tell, hopefully, because this experiment is continuing, we'll continue to get data. A second frontier in space-related research with LIP is the study of radiation effects, for instance, in planetary atmospheres, Mars and Jupiter. This was started again many years ago by young scientists at LIP. And when I first heard about this approach, I was concerned because at CERN we were involved in similar studies, simulating radiation damage on electronic components in the concept of LHC, and I knew how terribly hard this was. But this group was fantastically successful. This has spread, and they have many contracts with ESA, and I believe this was one part which contributed to the very successful collaboration of Portugal with ESA. Well, of course, as mentioned many times today, Gaspar's vision didn't stop at the detector. You have to develop, you have to process the detector signals and to work on them. And very successfully, he got involved, he and his collaborators got involved in Portuguese industry to work on very complex ASICs. This diagram was shown already. It's for the new CMS timing detector, a very complex chip where the TDC, the time to digital converter, has a timing resolution of 15 picoseconds, and Joao explained the importance of timing collisions at the upgraded LHC. Pier Giorgio, your turn. Here you advance, and here is the point.
Okay, so I will do my mistakes. Yes, you see on these transparencies a number of things which were very dear to the heart of Gaspar, but this is what was main interest in the last 20 or 25 years. I will start by telling a personal story. In a sunny afternoon in the 80s, I was having coffee with Gaspar and Rinus Verkerk at the CERN cafeteria, the one near the computer center. And we were discussing a thing which was very far from all of this computing technology. We were discussing the merits of the Motorola 6809 microprocessor, an 8-bit microprocessor, which for that time was capable of 16-bit arithmetics. And the two were debating these things, Rinus at that time was in charge of organizing the College of Microprocessors of ICTP in Trieste, and Gaspar at that time was a lecturer. I think he went on being a lecturer for 5, 6 times, I don't know, both in Trieste and going around the world. And we continue our discussion, and then we ended up in discussing society and science. And at the end, we were coming very much down to earth. We were discussing vineyards and rice fields in Piemonte, where I was coming from, and where their respective wives, Jana and Fedora, were coming also. But it has remained to me in my mind as something connected to Gaspar, somehow. So I will not speak of data processing and network because it has been dealt very much, but I will start from trigger, and let's see whether I advance. Yes. When one speaks of LHC experiments and their trigger conditions, I personally feel tempted to go back a bit. Computing in trigger was already used in the 70s, in the late 70s, but at that time, when you were processing on your computer the trigger which had been carefully selected by a first-level trigger, you were stopping the machinery and wait, that time. Now, the breakthrough that has happened with the LHC was that timeless trigger. You can store enough data for a latency time, and during that time you work it up with your first-level trigger, and then there is an event processing which follows. This was a great breakthrough at that time. Now, with the advances on special processors and the advances in lower price in memory, one is at the LHC now is moving towards another era in which you put more data on storage, and at the same time you do more processing online. Now, LHCb and Alice have given up with the custom design hardware trigger at all, and they are just doing computing with advanced computing, nevertheless, with FPGAs and GPUs and all of that, and they use just that for trigger, nothing else, and then they put all what they can on permanent storage. Atlas and CMS cannot make it because the rates are what they are. The rates in PP collisions are what they are, and they want to see the whole event. So they are improving in the sense that they put more processing in the first level trigger. The Atlas people call it L0 now because I think it's just a matter of terminology. But they put more processing in the hardware trigger, and then they also put more processing later on in the event selection. Now, it is very easy to say that you just have FPGAs and other good processors, and you have advanced software for them, but this is just the beginning. To use the FPGAs for this, you have to connect them to the input, feed the output, package them tightly, work with, take care of power, dissipations, and so on. And all of this is a major engineering work. It's not only computing work. It's a major engineering work to come up with a system. Although it's advanced computing, it's also baseline electronics. Now, for the high luminosity LHC, this trend will continue, but as you have heard from Tiziano and the others, it's going to be even more challenging. Good luck. Now, you have heard already about the major contributions of Atlas and CMS to R&D and deployment of the new trigger, so I will skip on that. Now, open data. Open data has been mentioned many times today, and I would like to give my view of open data. The Open Research Society there in the title can be generalized by saying open science. Fine. But the terminology in use is varied, and I will just go through it very briefly. You have data preservation, open data, data sharing, data reuse, data repurposing. All of these things have different connotations. Data preservation in our field, in particle physics, came a bit fashionable at the end of LEP, say 2000, when one was wondering what to do with the data that we have collected. But it was revived at the beginning of 2010-12 or so, by an ICFA initiative which was loosely connected to the stopping of the Tevatron. So it was, there was a study, and they came up with lots of recommendations. The trend is there, and the trend goes also to open data. But data preservation has nevertheless a number of questions which can be raised. Do you preserve the raw data, the process data? Where do you keep them? Who does the repository management? For how long? Hardware and software obsolescence? And last but not least, who pays for it? Now, there are independent organizations independent of us, like the European Commission or OECD, have also their saying on this topic, but I restrict my image to our world somehow. Now, open data is not enough. I have not invented the sentence. It's the title of a paper which appeared on Nature Physics at the beginning of this year, written by some people who are doing research in this field. Open data is not enough. You have the data, true, but then you have the metadata. Metadata, in my simple mind, at the beginning is the run number and the date. But there is much more, and there is never enough. It must be computer readable, but there is never enough. So you rely on knowledge. Where do you put knowledge? In the people, on papers, God knows where. And in my opinion, there are problems which are specific to high-energy physics. We are using a very severe trigger, which throws away a good part of the data, a good part, most of the data, and the trigger process is part of knowledge. So you have to understand and transmit this thing, and the other major problem is software. But this is not only ours. It's true that our software is big, but other people have similar problems in reusing software. Now, what is the view of reusing data, which is not only our problem? There is an example which is not quoted there, but in astronomy, they have been reusing data for more than a century. They have photographic plates that were exchanged between an observatory and the other. And so data reuse in that sense is started before us. But now it's being generalized, and And there are many other sciences that use it. Some of the sciences, particularly those which have to do with humans, have also ethical problems in reusing the data, but this is not the problem of high-energy physics. Now, I will quote by memory a sentence of a cynical researcher who said that in recent years there have been many more publications concerning the model and the rules and the meaning of data reuse and open data and data reuse than actual projects that reuse the data. This is a bit disturbing, but I think it's not a justification to stop, in my opinion, because we have there on a set which must be reused. Now, machine learning. I think we have heard about machine learning in many before, and I would only put a few questions. The first question is it a novel discovery method, or it's an aid to the traditional inductive method? This is one of the points which is debated by philosophers of science. And in speaking of machine learning and artificial intelligence in general, you are brought automatically to think of big data. It is true, as Jesus Marco said, that the big data hype is gone. However, in the general public, big data is what is the processing of lots of data collected from everywhere by someone, say Google, for its own interest, and maybe with a fallback on society. Now, in particle physics, we are in a better situation, because I don't think that the fact that we have big data changes the shopping habits of the physicists. So, and I would like to transpose to particle physics a sentence which I found and which I liked very much. Is a transpose from astrophysics to particle physics. In the field of astrophysics, the data collection does not affect the galaxies. And this should reassure people who are speaking of astrophysics. Now, we are using machine learning in many places. In simulation, the fast simulation now uses machine learning methods. In reconstructions, all of the networks that you use there, deeper knots, are there. And in analysis, you use that for feature extraction. So maybe we discover the next particle by just clustering a few data in the. Now, there is a concern by the philosophers of science about the opacity of the approach, and they have written lots of papers on this. And there was recently a conference on the epistemology on epistemic opacity in computer simulation and machine learning. And the subtitle of the conference was very illuminating: opening the black box and finding it dark. Now, there was a contribution by a project related to particle physics, and in particular related to Atlas, which to that conference, and it was the epistemology of the Large Hadron Collider. This is a project funded by a German agency in relation with Atlas. in relation, in loose relation with Atlas. And I read the paper, and it's interesting, but they don't speak of trigger at all. So they don't speak of the possible biases that are coming in from the fact that we had a trigger. And now, in the LHC, the trigger systems are using neural networks, and the neural networks have, by this business of, by these epistemic doubts, the neural networks use simulation. So it's a chain reaction that comes in the problems of the trigger bias. Anyhow, we are there. We use machine learning in all of the activities related to data in our experiments, and we better use it in the best way that we can. And here we have the Competence Center for Simulation and Big Data, which I don't, since I don't like the word big data at all, like Jesus there, I would call it Competence Center for Artificial Intelligence. No, for simulation and artificial intelligence. Okay, thank you very much. Now, Chris, no. It's not finished. It's not finished.
Well, briefly, we need to comment also on Gaspar's vision to get benefits to society. Medical imaging has been a long-standing tradition in particle physics, but the recent move towards establishing a proton tumor center in Lisbon is clearly one clear indication about the importance lip science has given to society, and we'll hear more about this. There are other, we have talked already about PET imaging. There's also a very strong program going on for environmental monitoring and clinical dosimetry, which is developing. And yes, I mentioned multi-gap RPCs for positron imaging. After LIP has built the brain scanner, the dream will be to build a full body scanner, because this is really what medical diagnostics would like to have. And I hope LIP will have the force, the vision, the perseverance to make this project happen. Another promising imaging concept is called ortho-computed tomography. Here you have, excuse me. Here you have a gamma beam traversing a phantom or a head, and you have detectors above and below to look at an induced gamma emission, which allows you to localize a tumor. In this case, this is a simulation inside the phantom. So this is another promising technology which could be used at such a proton tumor center. Pier Giorgio mentioned competence centers. This was another concept initiated recently by Gaspar and colleagues to bundle the vast experience scattered in many laboratories around Portugal and in the LIP laboratories, to bundle this competence and leverage it to help colleagues with it. One center is the Center for Monitoring and Control, based on LIP's vast experience in detector monitoring and control. And there one is developing these competences to help LIP groups, but also to work with industry on applying these concepts to industrial monitoring and detector applications. The other center is simulation and whatever you call it, big data. Pier Giorgio mentioned this already. Again, one is using the enormous competence, in particular in simulation, to help young aspiring scientists to get trained in these complicated business and to get up to speed very quickly. So, Gaspar's legacy. He instilled excellency, the spirit of excellency. He stimulated creative thinking. He had an unbound enthusiasm which he shared with his collaborators and the outside. He gave generous credit to his collaborators. In short, He was a shaker and mover of science in Portugal and beyond. He left us, but he left LIP as one of the world's leading laboratories, well prepared for a brilliant future. Thank you, Gaspar.